Today we continue our lessons with the properties of definite integrals. This is in the continuation of the lesson that we had before. And then after this lesson is quite short, fairly short, and then I want to discuss a little bit about the coming exam with you to find the proper time so that I can book the aula for that time. Okay, so let us start the lesson today. So we talked about definite integrals extensively, and now we want to talk about properties of definite integrals. So these are actually given in this theorem. So what are these properties? Some of them you can understand, some of them using the area interpretation of the definite integral, but in principle, if you remember, I told you that the definite integral is an abstract concept. It's a limit of a particular sum called the Riemann sum, and then whatever can be interpreted as the limit of a Riemann sum, it can be formulated in the language of integrals, definite integrals. Yes. Okay, so one thing that you need to know is if you have an integral from a to a, the answer to this integral is 0. Of course, if you want to see it from the definition point of view, which is actually the way that we have to do it, if you remember, we had this Riemann sum, k goes from 1 up to n, and then n goes to infinity. So this delta x, if you remember, was b minus a divided by n. But if the lower and upper limits are the same, so b and a are the same, so delta x is 0, and whenever delta x is 0, it means that all these terms are 0, and if I add them, it becomes 0. So this is something that you can immediately understand. Okay, I'm not going to motivate these theorems using the abstract point of view, but some of them you can understand it from the area point of view. Okay, so number 2, this is also something that you need to know, but some books write this as the definition, some books write it as the theorem. So let us just put all of these properties as theorems. So this tells you that if you have an integral which goes from b to a, by the way, when I say x goes from a to b, it means that a is smaller than b, yes? But now here you see that I have an indefinite integral for which b, the lower limit, is greater than the upper limit. Anyway, if you want to, you can interchange these two numbers, but you need to put an extra negative sign there. So this is always possible. This is a little bit counterintuitive because this is why some books call this the definition of the definite integral when the lower limit is greater than the upper limit. But of course, this is also, I saw it in the book, this is a level 3 problem in the book. So one way to understand this is using the Newton's formula. So let me write this down and I will clean it. So for example, if I ask you what is the integral of a to b f of x dx, do you remember? You would answer capital F of b minus capital F of a. In that way, if I ask you what is the integral from b to a, this is the solution that I saw in the book anyway, so then you would say this would be f of a minus f of b. Yes, do you remember that was Newton's formula? And then of course, if it is from a to b, the answer would be this. If it is from b to a, the answer would be this. Now if I ask you what is the difference between these two expressions, you would say one of them is negative of the other one. Yes, so this means that this integral is negative of that integral. This is also understandable using the definition because you have from a to a, so this means that you write f of a minus f of a, and f of a minus f of a is equal to 0. Okay, so let me clean them, we don't need them to be here. Okay, another property is that if you have if you want to calculate an integral of this combination in which c is a constant multiplied by a function, and you want to calculate this, what you can do, you can pull this c out, and it becomes from a to b of that function. Again, this is also understandable. Why? Because, for example, if I ask you, for example, let us capital F, be a primitive function for little f. Now, do you remember I told you that if I ask you what is a primitive function for a multiple of that, a primitive function of that would be c of f. Now assume that capital F is a primitive function of f. We learned that c times capital F is a primitive function for c of f. And now, using Newton's theorem, if I want to calculate integral from a to b cf of x dx, you write the primitive function and you write it from a to b, but then what happens? It becomes c f of b minus c f of a. Then I can factor a c out. It becomes f of b minus f of a. But if I ask you what is this, you would say this is the integral of just the function f, and then you see it's multiplied by a c. So if you want to understand these theorems, you can use the Newton's theorem, okay? But the reason that I don't want to use the Newton's theorem, because you see that I have written integrable. A function is integrable whenever this integral exists. This is not always the case that whatever function that you write, its definite integral exists. One possibility is that the function is continuous. It has been shown in more advanced mathematics, if a function is continuous on the interval that you are investigating your definite integral, then it is guaranteed that its integral also exists. I don't want to discuss a little more about this because it would be quite advanced. Because if you remember, I told you that when we write the Riemann sum, I told you that you have infinitely many degrees of freedom when you want to choose this ck. But I didn't talk about this, but it is a very, very technical problem. How do we know that this limit will not depend on my choices of these numbers? It is not clear. If this function, if this limit does not depend on the numbers that I am choosing within these intervals, then this limit exists and it's unique, and that number is called the integral, and this function is called integrable. Okay, so don't worry about these things. I don't want to bother you about this. So this proof that you see here only works if my function is continuous, because Newton's formula works if the function is continuous on the interval that I am interested in. Okay, but even if the function is not continuous, it might still be integrable, and then these formulas are again valid. Okay, so this is the real stuff, but you don't need to be worried about that. You can see that these are the properties of definite integrals, and any function that you will be concerned in this course follows these rules. Okay, and for example, you have this situation as well. Integral of the sum of two functions, you can decompose your integral and write the integral of the first one plus the integral of the second one, and the same for the difference of two functions. These are again easy to prove. For example, let us have this capital F a primitive function for f, and then let us have the capital G a primitive function for g. So do you remember, if I ask you what is a primitive function for f of x plus g of x, if you remember, this would be capital F plus capital G. Now I want to calculate this integral. So I will ask myself, what is a primitive function for this? The answer is this. What I do, I write from a to b, so it means that I put b instead of x, I put a instead of x, and then subtract these two numbers, yes? So then what happens? It becomes f of b. This minus sign goes here, it becomes minus f of a. I write them next to each other. And then I will have g of b minus, I made a mistake. Yes, this is not f, sorry. This is not f. This is f of a. This is f of a plus g of a. That was my mistake, yes? Because this is my primitive function. I need to replace x with b. I need to replace x with a and subtract them. But then f of b minus f of a, I wrote them next to each other, and g of b minus g of a, I write them next to each other. But now if I ask you what is this, you would say this is the integral from a to b, f of x dx. And if I ask you what is this, you would say this is integral from a to b, g of x dx. And what was this one? This was the integral of f of x plus g of x. So this is a proof for the case that I can use Newton's formula. Newton's formula only works if the function is continuous in that interval of integration. Okay, so another thing that is important to know, again you can immediately understand it from here, and that is a very important property of definite integrals. It tells you that you can break into one integral into more integrals if you want to. So for example, if I want to calculate the integral of x from a to b, if you want to, you can break it into two parts. You can go from a to c and calculate this, and then from c to b, and then add them together. It will give you the same answer. It's good to see it from two perspectives. Let us first understand this formula using the area interpretation. So for example, assume that I have this situation. I have this function f of x, and then I have a and then b. In this interpretation, it makes sense if I put c somewhere between a and b, of course. Okay, and then this integral here gives you the area that I am right now showing to you. This is the whole area from a to b, yes? But now what is the area from a to c? The area from a to c would be this part, and the area from c to b would be this part. So it is clear that if I add these two areas, it becomes the area, that the total area, which can be represented by this integral. This is one way of understanding that. But of course, more rigorous way of understanding this is again using the Newton's formula. Okay, so for example, let me start from the right hand side here. The reason that I am cleaning them because the proofs are not important for you. Okay, the only one that I saw in the book is this one. Okay, so at the right hand side is the integral from a to c, and then the plus integral from c to b. But let us assume that capital F is a primitive function. So this would be the capital F from a to c plus capital F from c to b. But what is the first one? The first one is f of c minus f of a, plus the second one is f of b minus f of c, but you minus f of c. But then you see that this minus f of c and this positive f of c are gone, so you get capital F of b minus capital F of a, and that is exactly equal to the integral between a and b. Yes, and that is the right hand side, the left hand side. You see, in this way, you don't need to assume that c is between a and b. Even if c is not between a and b, this proof is independent of the location of C, because wherever C is, we don't care. F minus f of C and f of C are gone. It doesn't matter if C is between A and B or outside A and B. So remember, this is also a very important formula. These formulas are not important if you want to calculate the integrals. So for example, let me also mention this here. For example, if you want to calculate integral from 0 to 1, x squared plus x dx, I don't calculate it. So in principle, according to this rule, I can break it into two parts, x squared plus integral 0 to 1 x dx. But we don't need this to calculate this integral. You can calculate this integral and add them together. But do you remember, if this is given to you, even myself, I don't do it in this way. I prefer to find a primitive function for my function, so I do it in one place. It becomes x to the 3 over 3 plus x to the 2 over 2 from 0 to 1, and then just calculate this one. Of course, it doesn't matter if you calculate it in this way, but what I'm saying is that the power of these rules are not because calculating this integral becomes simpler. These are the properties that you need to know that this definite integral will follow. Okay, I will give you examples that you have somehow to use these formulas. Okay, so let me just clean this one as well. Now, the two things that I want to mention here, it's not directly mentioned in the book, but you can combine these properties into one bigger formula. So if I have this combination, I have n functions instead of two functions, and then I have some constant being multiplied by them, positive or negative, it doesn't matter. If I want to calculate this integral, if I want to, I can decompose it into n integrals and I can pull these constants out. Yes, so you see that this constant can be pulled out. The reason that I am pulling these constants out is because of this part. And the reason that I can split it into more integrals is because of these two theorems. And of course, this is for two functions, this is for n functions. If I want to be very rigorous in proving this, I have to use mathematical induction, but that is very, very trivial. Okay, and the other thing is that this is not only for two numbers, only for one number in between. You can break the integral if you want to more than two integrals. For example, if you want to go from integral from a to b, you can go from a to some number c1, go from c1 to another number c2, and continue this process, and finally, if you want to, you can go from the final number to b. For example, if I want to go from 0 to 7 of an integral, if I want to, I can go from 0 to, I don't know, 5 f of x dx. I can go from 5 to 10 f of x dx, and then I return from 10 to 7 f of x dx. So this is also a valid decomposition. So this theorem tells you, this remark tells you that you don't need to just do it, decompose it into two integrals. You can decompose this into many integrals that you want, any number of integrals that you want. Okay, so these properties are given in the formula sheet, but these are very important to remember, I think. Okay, let us see how we can use these theorems in some problems. That when do we actually need them? So one example that I was thinking about was something like this. Okay, so this is telling you that assume you know that this integral is pi over 4. Of course, this is not very hard. If you are following the lectures, in principle, you should be able to calculate this and confirm that this is exactly pi over 4. And I think it's a very good exercise to do that. If you don't remember, you need to go back and review some videos or lectures to see how we can calculate. If you remember, when I was talking about primitive functions, I told you how to find a primitive function for cosinus, or for sine and cosine squared. This is one of the previous lessons. But here I am giving it to you, so I am making the problem much easier for you. I am telling you that assume that someone has already calculated this integral and that person got the answer pi over 4 for that integral. Based on this assumption, can you calculate this definite integral? Okay? So let us see how can I solve this problem if that assumption is given to me. So I would say that I want to find, this part is easy because 2x, everyone knows how to find the primitive function for that part. The primitive function for cosine squared is a little bit technical, even though you should be able to do it. But what is the connection between cosine squared and sine squared? So that's the motivation. So I would say that the integral from 0 to pi over 2, 2x minus 3 cosine squared x dx. The motivation behind what I am doing now is because I want to find a connection between my question mark and the assumption given in the problem. So I would write it as 2x minus 3. If you remember from trigonometry, instead of cosine squared, I can write 1 minus sine squared. And then, of course, I have dx. Let me simplify what is inside. So this becomes the integral from 0 to pi over 2. Then I have 2x minus 3 plus 3 sine squared x dx. Okay? So it's good now. But what can I do? I can decompose this integral into two parts. Yes, I can write it as integral from 0 to pi over 2. For example, I can take this first function to be this. If you want to, you can decompose it to more integrals, but it is unnecessary. I will decompose it into 2, and the next one I pull the 3 out, and I will write from 0 to pi over 2 sine squared x dx. Okay, just let me wait a little bit. Is everything understandable here? No questions? Okay. You see, the easy part, I can do it myself. This would be a little bit hard part, but I don't have any problem with that right now because this is just given to me. Okay? So what I can do now, I can write it as I will find a primitive function for this. Hopefully you immediately know it's x squared minus 3x. And then I would write it goes from 0 to pi over 2 plus 3 times, this is directly given to be pi over 4, so I multiply it by pi over 4. And then what I do, I put pi over 2, so it becomes pi over 2, 4 minus 3 pi over 2. I have to put 0 as well, but when I put 0, everything vanishes, so minus 0 I don't need to write. And then I will have plus 3 pi over 4. And now if I want to simplify that, so it becomes pi squared over 4. And the other one is minus 3 pi over 4. So for example, I can, I don't know, factor a pi over 4 out, then it becomes pi minus 3. So that would be the final answer. So you see, this is one of the applications at the level of your lesson. This is one of those types of problems that you may face in this course. An integral is given to you, which is usually hard to calculate, and then another integral is asked from you. So you see, I used the theorems today. I wrote this from here to here to here is just the old lesson. It is trigonometry. And then when I decompose this integral into this form, this is today's lesson. Okay, so this is the only part that is today's lesson. Everything that I have done so far is the previous lesson. Any questions? Okay. So let us go to the next problem. For example, here, I have asked you to calculate I given in the following form. Of course, you might say that I don't have any problem with that, but if you start doing this, then you will face problems here, because tangent squared is not something at the level of your lesson how to find a primitive function for that. But if you are not in hurry and try to see that, okay, when I combine these two, this hard part is actually gone, and what is left for me is 1 plus tangent squared, and in principle you should know the primitive function for this. Okay, so here I am doing the opposite direction of the formula, yes? So I am writing this I in this form. I would say that I is equal to integral from 0 to pi over 4. So it is very important to see that the limits are exactly the same. Otherwise I cannot use that theorem. So integral from 0 to pi over 4, then I will write 1 minus x squared as my first function, plus x squared plus tangent squared x as my second function, then dx. This is today's lesson. This tells you that I can combine these two integrals into one integral. What is the benefit behind that is because this minus x squared and this positive x squared now are cancelled. So what is left for me is from 0 to pi over 4, 1 plus tangent squared x. Yes? Okay, now if I ask you how can you calculate this, this should be familiar for you. Yes? What is a function whose derivative is 1 plus tangent squared? Do you remember? One plus tangent squared. If you don't remember, let me write it. There is another name for this. I think these are very famous equations. Sooner or later you have to memorize them. So if you go to technical universities, of course. 1 plus tangent squared x is 1 over cosine squared x. This is a famous formula. We proved it when I was teaching you trigonometry in chapter 2, okay? So now, can you tell me what is a primitive function? This is a famous one. What is a primitive function for 1 over cosine squared? No idea?
ln.
No, not ln. No, it's not related to ln. It's related to, no one remembers?
Tangent of x.
Yes, tangent of x, thank you. So this is tangent of x. So this becomes tangent of x. And then it goes from 0 to pi over 4. Then it becomes tangent of pi over 4 minus tangent of 0, but tangent of 1 pi over 4 is 1, tangent of 0 is 0, so the answer would be 1. Okay, so for example, let me just test your knowledge. So might be, I don't know, might be in some exam they ask you about this. What is this integral? Now I know, do you know the trick here? Can you tell me how should I calculate this now? For example, you see that a primitive function for 1 plus tangent squared x is known. Okay, so what you can do, you can write it in this one way you do to solve this problem is to write 1 plus tangent x squared and then negative 1 to compensate for that 1 that I am adding. Now I can imagine this as my function f minus I can imagine this as my function g. Now I can decompose the integral into two pieces. The first piece becomes this. The second piece becomes this. Of course, we don't write 1 if you don't want to. But now if I ask you what is a primitive function, the answer is clear. As you told, it's tangent of x from 0 to pi over 4. And then what is a primitive function for 1? It is x. The derivative of x is 1. It goes from 0 to pi over 4. So then it becomes tangent of pi over 4 minus tangent of 0 minus pi over 4 minus 0. Tangent pi over 4 is 1, tangent of 0 is 0. pi over 4 minus 0 is just pi over 4, so the answer becomes 1 minus pi over 4. So you see, these are important tools in your hand, so if you want to calculate these integrals, you can use these tricks. Of course, I'm not saying this is always easy, but for these problems, they are not very, very hard. Okay, any questions? Okay, another type of questions, for example, you see here, this is one of those questions that there is no other way to solve this problem except that you use these properties. Because how do you want to calculate this? Because you don't know anything about the function f, so you cannot use the Newton's theorem here. Okay, so if I want to calculate this, I have to use this information given in the problem. Okay, and then you see that the limits are different in different integrals, even though the function is always the same. So do you have any idea, for example, how to answer the first one? How can I answer, do you think, about this?
Sum of the second and the third.
Yes, why? Because the integral from 0 to 5 can be decomposed into two parts. If from 0 to 2, f of x dx, and then from 2 to 5, f of x dx. Of course, you might ask, why did I break this integral into these two parts? The answer is clear, because I have some information about this and I have some information about this. Of course, if you want to, you can break it from 0 to 1 and then plus 1 to 5, but this is useless because I don't know anything about this, I don't know anything about this. So this is the most efficient way of breaking this integral into two pieces, and then you see this is the only way to solve this problem. Okay? There is no alternative for this. And so the first integral here is from 0 to 2, it's given to be 5, so it becomes 5. And then from 2 to 5, it's given to be 6. So I add them, the answer becomes 11. Okay, now what do you think about 5 to 7? Sorry. Any ideas?
The first one minus the second and third ones.
I cannot immediately realize that, but how do you break that? Can you tell me from 5 to 7, what do you write? From 5 to 2 and 2 to 0 and 0 to 7. Yes, I think this will work. From 5 to 2, yes, and then from 2 to 0 and from 0 to 7. First of all, do you agree with me that this is the legitimate way of breaking the integral? So do you remember I told you can break one integral into more integrals, but then the first integral starts with the lower limit, the final integral ends with the upper limit, and these numbers should come in crossway, yes? So from 5 to 2, from 2 to 0, from 0 to 7. You might say, why did I do this? Yeah, you need to have a little bit of experience, but this is not extremely hard, because the numbers that are involved are 0 and 2, and so I was able to see this pattern. But then this is not a problem that 2 is up and 5 is down, because I have another rule. Do you remember the second one? I can write a negative sign here, and then I can interchange these two. So this becomes 2 to 5 f of x dx. Okay, and then for the next one I do the same thing. I put a negative sign and I interchange these two. But I don't need to change anything for the next one, so I keep it as it is. Yes? And now, if you see, I have negative sign. This integral is directly given in the problem. It is 6. So this becomes minus 6. And then integral from 0 to 2 is given to be 5. I have a negative sign behind that, so it is negative 5. And then integral from 0 to 7 is given to be 3. So the answer to this would be minus 8. Or might be you are able also to find another way, but that is one way of doing that. I want you to understand this is the correct way of doing it. Any questions? Okay. Now let us go to this problem. I want to wait a little bit for you. I think this is also the same, more or less the same example. I can wait a little bit for you. Okay, what's the final answer? Okay, can you tell me how should I break this integral so that I can use the information provided for me?
We start with an integral from 1 to 2 for x dx plus integral from 2 to minus 3.
Exactly. Yes, but is it useful? Yes, because here I want to use this piece of information. I need to interchange these two, so the price that I have to pay is to put a negative sign there. Yes, and what is the next one? The next one is exactly as I want to. Yes, and then it means that this becomes negative 4 plus 7, so the answer is positive 3. So I think it's very simple. It's very simple to see how to solve these problems. Any questions? But a little bit higher level question that you need to know is this type of problems. So you have a function with more than one rule. This tells you that if the input is 4 or greater than 4, this rule is used for this function. If the input that you provide for your function is less than 4, this input should be used. For example, if I ask you what is f of 4, you need to replace x with 4, but which x? The x here. Because 4 satisfies this condition, so it means that I have to use this rule. So it becomes 4 plus 1 is 5. I'm just recalling you about these type of functions. If I ask you what is f of 5, you need to replace x with 5, but again this x in this rule, because 5 is an input that satisfies this condition. So this is read in this way. F of x is x plus 1 if x is greater than or equal to 4, and it is 1 minus x squared if x is less than 4. Now I am calculating f of 5. This is not part of the solution. This is just reviewing something about this type of functions. So f of 5 is what? It's 5 plus 1 again, so it is 6. But if I ask you what is f of 0, I need to replace x with 0, but for this rule, because 0 is less than 4, so I have to use this rule. So this becomes 1 minus 0 to power 2, so the answer is 1. Now that you understand what is the meaning of this function, so I have given you a function with two different rules, and I am asking you to calculate this integral. But you need to know which function you need to replace here, because f of x has two different rules. And the interval is from 0 to 5, yes? So if I want to imagine it, for example, if this is the x-axis, I don't know, for example, here is 0, here is 5, for example, 1, 2, 3, 4, 5, and then this number is 4, okay? Before this 4 everywhere, the rule is x plus 1. After this rule everywhere, the rule is 1 minus x squared. If you were supposed to integrate somewhere here, that was not a problem. You just use this rule. If you are supposed to calculate the integral somewhere here, for example, there is only one rule. But now you have decided to calculate the integral from 0 to 5. One part of it follows this rule, the other part follows this rule. So it depends. This theorem that we just talked about will come to our help, yes? So it means that this is a natural motivation to break this integral into two integrals, yes? So I would say that my goal is to calculate the integral from 0 to 5 f of x dx. But now I know that after 4 and before 4 the function follows different rules, so this motivates me to break the integral from 0 to 4 f of x dx and then plus 4 to 5 f of x dx. Yes? Here it means that x is somewhere between 0 and 4. And you don't need to be worried about equalities, because one point, excluding one point from the interval does not change the value of the integral. And that is understandable, yes, from the area interpretation. So assume that I want to calculate this area from this point to that point. It doesn't matter at all if I am including the line or I am excluding one line, because the thickness of a line is 0. So if I add that line or exclude it, I am not changing the area at all. So don't be worried about these final points if they are included or excluded. What matters is that in this integral, x is between 0 and 4. So it is less than 4. When it is less than 4, for the first integral, I have to use the lower rule. And then for the next integral, x goes from 4 to 5. It means that x is greater than 4. So it means that I have to use the first rule. And then it means that I have two integrals to calculate. I have to calculate them separately. I would say this is the most important application of this theorem, that you can break the integral into sum of two integrals with different limits. Okay, so then you don't need to be worried. So you need to calculate two integrals. So for example, let me call this one I1, the first integral, and then this one I2. You calculate them separately and add them, yes? Okay, so how should I calculate the first integral? I need to ask myself, can I find a primitive function for this? It is super simple, so it becomes equal to x minus 1/3 of x to the 3. This is a primitive function for my function, so it goes from 0 to 4. I put 4 and then I put 0 and subtract them. So I1 is minus 52 over 3. Calculating I2, so I2 is a primitive function for this function is x squared over 2 plus x, and it goes from 4 to 5. So I put 5. it becomes 25 over 2 plus 5. I put 4, it becomes 16 over 2 plus 4, and I subtract them. So what's the answer? So it's 35 over 2 minus 12, so it is 11 over 2. And then finally the question mark, so let me write it here. So the question mark is I1 plus I2, which is equal to minus 52 over 3 plus 11 over 2. And then the common denominator would be 6 minus 104 plus 33. So it is negative, the denominator is 6. How much is that? 171. Yes, so that would be the answer to this integral. So is there any questions here? Everything is understandable? Okay. The final example is more or less the same idea, but in a disguised form. Yes, so here I'm asking you to calculate this integral, but there is an absolute value sign here. If it was brackets, it was super simple. It's just E-level question in Math 3C. If I ask you this, a primitive function for this, and we know, and then we usually immediately use the Newton's formula. But we don't know any primitive function for the absolute value of x minus 1. But we know something else for absolute value. So do you remember? Absolute value is actually a very bad thing in mathematics. It is always, it's needed, so we cannot ignore that. But whenever we want to do with the absolute value sign, we need to get rid of absolute value sign first. And you cannot get rid of absolute value sign unless you know this definition. If I ask you what is the absolute value of something, a box here, you would say the answer becomes the box itself if what is included in the box is greater than or equal to 0. So if you are certain about the positiveness of what you see in absolute value, you actually don't need it, just throw it away. If you are certain about the sign of this and you are certain that this is negative, you still can get rid of the absolute value sign, but the price that you have to pay is to put a minus sign there. If this expression is sometimes positive and sometimes negative, you cannot just simply throw it away. Either you have to keep it, or if you want to throw it away, you need to write it in this more complicated form. This is why people prefer to write absolute value in the first place, because otherwise they'd have to write a lot. Okay, this symbol by itself is sitting for this expression here. Okay, so am I certain about the sign of x minus 1? I would say no, because if you draw this x-axis, so you are interested, so assume that this is 0, this is 1, for example, and then this is 2 and 3, and this is minus 2 here. Okay, so this is the interval of integration that you are interested, from minus 2 to 3. You are interested in integrating your function here. But x minus 1 on this side, x minus 1 is positive. Do you agree? Because x minus 1, when I am looking here, x is greater than 1, so x minus 1 is positive. When x minus 1 is positive, do I need absolute value sign? The answer is no. I can just throw it away. Yes? But there is another part of interest here. There is this part that x is less than 1. So what happens on this part? On this part, x minus 1 is negative, because x is less than 1. And then it means that, can I throw absolute value sign away? The answer is yes, but the price is this extra negative sign. So the answer would be minus x minus 1, which is 1 minus x. So this motivates me exactly as before. So I can break my integral from minus 2, so I don't have this I here, minus 2 to 3, absolute value of x minus 1 dx. So I break my integral from interval from minus 2 to 1, absolute value of x minus 1 dx, plus 1 to 3, absolute value of x minus 1 dx. Okay, but here on this interval I am certain about the sign of x minus 1. X minus 1, when x is smaller than 1, is definitely negative. So can I remove the absolute value sign? The answer is yes, but you need to multiply it by a negative sign. I have already done that, so this is the answer. And the other one, can I get rid of absolute value sign here? The answer is again yes, because now I am going from 1 up to 3, x minus 1 is positive, so I can just throw it away without any changes. But could I throw absolute value sign away here? No, because here I am going from minus 2 to 3. On some parts x minus 1 is negative, on some parts x minus 1 is positive. So I have to keep it. And then I think this is very simple for you now, because these integrals are actually elementary integrals. So the first one is x minus x squared over 2. It goes from minus 2 to 1, plus the next one is x squared divided by 2 minus x, but it goes from 1 to 3. Don't get confused. You're not allowed to simplify this with that and this with that, because the boundaries are different. So how should I calculate? So let me just go to this technique. So I put 1 there, so it becomes 1 minus half, it becomes 1 half. I put minus 2 there. Yes, so I put 1 instead of x, I calculated. I put minus 2 instead of x. Let me double check. Yes, that's correct. And then the other one, I put 3 there, it becomes 9 over 2. 9 over 2 minus 3. So what is that? It is 3 over 2. Yes, and then I put 1. It's minus 1 over 2. What I have to do, I write the number above minus the number below for the first one, the number above minus the number below for the second one, and then patiently calculate these. So it becomes 4 plus 1 half, it's 9 over 2, the first one. The second one is 4 over 2. So it becomes 13 over 2. So that is the final answer that you get. Okay, is everything clear? So these last two questions, I would consider them as A-level questions for this part, but other parts are actually very simple. Okay, so if you don't have any questions, thank you. I will stop this recording.